So we want to design a universal binary counter. This here is a table that describes how the counter works, so let's go over it quickly here. So let's start with the case when clear equals to 1. When clear equals to 1, all other variables are x's. In other words, they are don't cares. So the load is an x, the enable is also an x, and the up down is also an x. So that means that our Q next state is going to be equal to the lower bound or variable LB. I'll explain later on what LB stands for and the bigger picture. So let's move on. When we look at the case when load equals to 1, we see that the enable variable and the up down variables are also don't cares. So what that means is that our Q next state is going to equal to D. In other words, we're going to be loading the variable by the name of D right here. That's what the operation says here. If we move on, we have the enable function. And if it is 1, depending on UD, so if we have enable equal to 1, we can either have the counter count up from LB to UB or count down from UB to LB. So LB and UB stand for upper bound and lower bound. So these are the variables that I'm talking about. So in our last case, if we have enable equal to 0 right here, that simply means that we're going to have a pause in the counter. So now let's go over what these variables actually mean, right? So LB stands for lower bound. UB stands for upper bound. And D is simply a input variable. So what we need to make sure that we understand is that if we have a lower bound and an upper bound, that means that the input variable can be outside of the range of the lower and upper bounds. So we need to make sure that D is within the lower bound. And upper bound. Like that. So just to sort of reiterate what we have here, let's bring this to the right. And then we have here. Let me rewrite that. Input variables. Right there. Okay, so here we are in Modelsim, and I've created the new project and I've added some new files. I've added a file named univbincounter.sv and another file which is the test bench, and I've named it univ. This is called universal binary counter, but I've made it shorter. So let's go ahead and edit this one here, and let's begin our code. And let's not forget what we want to design. We want to make this counter, and we want to have these specifications here. So let's go ahead and begin. All right, so we want to create the module. And then we also want to create a parameter. All right. And then we do have a couple of variables to declare as well. So let's go ahead and do those. We have the clock. We have the reset. We also have the clear. We have the load. We have the enable. We have the up-down variable. Let's see. And then we want to make sure that we're making use of the parameter here. Obviously, the default parameter for now is going to be 4 because I made it that's what I made it in the beginning. And then we have the input logic, and this is the variable for what we want to load. And as we move along, now I want to declare my upper bound and lower bound. So these are going to be the same sort of dimension. I had an extra 0 there. So upper bound and then lower bound. and then I want to declare my output logic. So then I want to call something here. I want to make a variable called maxTick. In other words, when the counter reaches the maximum. And then I want another variable called minTick. In other words, when the output reaches the minimum. And then I want the actual output. All right, so that is going to be Q. So that does it for my variables. Now I want to declare some interior variables here. So these aren't inputs or outputs. These are going to be used for the module itself. So we have our register, and then we have our next. So current state, this is basically another way of saying current state and next state, because we are dealing with a sequential counter. So we need to make sure that we have these two variables here. And then we're going to have an additional variable called capital D, and we're going to see why in a little bit. And then we need to declare a always FF. This is for the flip-flop, right? And then we want to make sure that the clock triggers on the positive edge, right? Did I write that? Okay, there we go. As well as the reset. Okay. All right, so if reset is high, what does the clock do? Well, I don't know why I keep putting capital here. The current register is going to be less than or equal to the lower bound, right? Because basically, I want it to reset. So my default reset value is the lower bound. Typically, this value here is 0 because that's how flip-flop works. But in our case, it's going to be a lower bound. And then I say else. Or edge less than equal to our next. Like that. So now we can start we can begin to worry about like how we relate our next to our next. Sorry, I meant how we relate our edge to our next. Okay, well, let's continue now. So now we need to make sure that in this block, we're gonna make sure that the variable D is always within the upper bound and lower bound. So I'm gonna say if D is greater than upper bound, then let capital D equal to upper bound. So in other words, if D is higher than the upper bound, then just reset D, or rather, create this new variable and then set it to the upper bound. Else, if D, and let's put some spaces here just so we make it look nice. Else, if D is less than lower bound, like that, then we simply set capital D equal to upper bound, or rather lower bound, sorry. Else, so this is basically in any other case, if it is actually within the range, right? Well, D is just going to be equal to lowercase d, just like that. So now the next thing we want to do is we want to create the main body of the code. In other words, the code that performs the actual counting, and also the code that monitors the variables like clear, load, enable, and the up-down variable. So let's go ahead and declare another combinational block here. If clear, then our next is going to be, that's right, the lower bound. Let's take a quick look at our design here. So if we said that if clear is equal to 1 here, we're going to have the output Q next state equal to the lower bound, and that's what we have going on here. And we're going to basically be following this same logic, and then once I'm done making this code here, we can compare it. So let's keep going. else if load is high, so that means our next is going to be equal to D, capital D, right? Because we're referencing these capitals here. Else if enable and UD are 1, and then here we're going to have an additional if statement here because of the upper bound and lower bound. So in the case that our next is equal to the upper bound, here's what's going to happen. I'm going to let our next equal to the lower bound, like that. Else our next. So in the case that our next is not equal to upper bound, then we just simply say our next is equal to our edge plus 1. So in other words, this is the performs the action of counting up. Else if enable and inverted UD. So when UD is 0, here's what's going to happen. I'm going to have another if statement, and then I'm going to be looking at our next. And if it is equal to lower bound, I have to reset our next to the upper bound, like that. Else, oh, we're not going to have no parentheses. And then we have our next is going to be equal to our edge minus 1. All right, because we're going to be counting down here when UD is equal to 0. Let's not forget that. And in all other cases, in other words, the only case that remains is when the enable function is 0, we're simply going to have a pause in the counter. So we're going to have our next equal to our edge, right? And let's just, I guess I can just say that this is a pause. And let's also make a comment here that this takes care of D values if they are out of bounds. Okay. So let's continue here. Now what I want to do is I want to assign some important variables here. I want to make sure that the output is equal to our register. Q, the output is equal to our reg. So let's write that. And let's just to reiterate, Q is the output. Like that. At the same time, I want to declare some other variables. Max tick. So this one's going to be a little bit interesting because our tick is basically when the register reaches the upper bound. Right? So I'm going to have a conditional statement here. Okay, so let's write it out here. I'm going to have a question mark here. And then we have a binary value of 1, like that. And then another binary value of 0. So what this basically says that I want max tick to equal 1 or 0 given this case. So if this case is true, I want max tick to equal to 1. If this case is false, I want max tick to equal to 0. So this is how the statement works. Similarly, I'm going to assign a value for min tick, minimum tick, right? And I'm going to say our register equal lower bound question mark 1 binary 0. So let's go over it one more time. I want min tick to equal to 1 or 0 given this case. So if this case is true, if our register is equal to lower bound, then min tick is 1. For all other cases, when our reg is not equal to lower bound, main tick is going to be equal to 0. So now all we need to do is just end the module. And so this finishes our code. And then I want to save it. Okay, so I've compiled both of these codes now. I already made test bench. This test bench, I'm not going to talk about it in this video. I'll talk about this test bench in the in the next video, because this has to do with more advanced methods of verification rather than simply looking at the timing diagram. So what I'm going to do now is I'm going to simulate this. I'm going to start simulation for the universal binary counter test bench, and then I'm going to press OK. And so that should give me that starts loading. And then I need to select my variables now. So in this case, since we're not going to be looking at the test bench, we do need to look at the timing diagram. So I'm going to select some variables now. Let's see. The waveform, I wonder why it's like that. I want it here. Okay. So let's go ahead and let's add some variables here. Let's see. Oh, why is this like this? All right. So the first thing I want to add is the clock. Then I want to add the reset. Then I want to add the load. Then the enable. And let's see, I want to add the up down as well. So I'll add those two. I want to add the D variable and the Q variable. And then I want to add the upper bound and the lower bound. And while we're at it, let's add the max tick and min tick. And these 4 variables, these are going to be unsigned integers. So let's put it like that. So now let's run this thing. Let's change this to 100 milliseconds. Or run it. And let's run it now. Okay. So this is what it looks like. It seems like we have an error here. And right in the very beginning, we see we have a D. It is has a value of 3. We have the load function is going high, but then my Q is not going to 0. So if you go back to my counter here, turns out I made a mistake here. D must be less than lower bound here. So now I have to go here. I have to make sure I save these changes and then recompile them. All right. And here is the interesting part. My comprehensive test bench that tests the code through assertions detected the error. And so this, tells me that I have a nice test bench. But in the next video, we will be talking about that test bench because it is very interesting. Okay, so now let's take a look at this timing diagram here. So we have here, we have 3 for the D variable, and then from what we remember, let's take a look at the right here. So we said that if load is equal to 1, the enable, the up down, and the Q next state. The enable and the up down is X's, so that means we don't care what they are. And then the Q next state is going to be equal to D. So let's see what we have here. In the next clock cycle, we see that actually that is what happens. Q becomes 3 right here, given that we have a load of 1 here. We also see that this enable is 0 all throughout here. Up until this point, we see that we have declared new input. We have declared new lower bounds and upper bounds. Okay, so here we have some new lower bounds and upper bounds, and we see that 4 is set to, not 4, Q is set to 4 even when the enable is not on. Alright, well that's because we need to make sure that that D is not out of range. So what's going to happen is that D, this value here, goes into the counter, but then it sees that it can't be that value, so then it makes the output equal to 4, right? Because D is less than the lower bound, so it sets it to 4 here. So now finally we have enable is equal to 1. So then at this point forward, we're going to start counting up, right? Because we have the UD variable is also equal to 1. So the up down variable is 1, that means count up. If the up down variable is equal to 2, that means count down. So let's see. Here we reach 10. which is the upper bound of the counter. At that point, we see max tick goes up, and then we see a reset back to 4. In other words, back to the lower bound. And then we see that the min tick goes up by 1 here. And then it counts back up. So in essence, this counter is counting from 4 to 10, and it's repeating. So it's doing what it's supposed to. So let's move on here to the next part of the waveform. Here we have new upper bound and lower bounds. We have a lower bound of 0 and an upper bound of 15. Right? We see that the load is equal to 1. And then we see that D is equal to 15. So that means we're loading 15 into this counter here. And then the load goes back to 0. We see we have the enable is 1, and then the up down is 0. So what that means is we should be counting down, right? So let's see. Start at 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. And then 15 again. So that's good. And then right here, we have a sudden change of upper bound and lower bound. Right here. So for a moment here, we have 14. This is incorrect. It should count down to 2. So let's see what happens. Let's look at the other signals here. And why is that the case? We have an enable here. So right after this clock cycle, right here, it goes back to 2. And then it counts from 2 to 13, right? So we have, so then, and let's see, this is so up, so it's going to be counting up, right? So it's 2, 3, 4, 5, 6, 7. And then at this point, we have something interesting happening. We have the enable function is going to be 0, so it's going to pause. It's effectively pausing the counter here. And at the same time, we have a load function coming in here. So it's pausing and then it's loading. So we see that 5 gets loaded into Q. And then the load is turned off and then the enable is turned back on right here. So then it's going to be counting back up. Right? So it's going to go 5, 6, 7, 8, 9, 10, 11, 12, 13. And then back to 2 because of our upper bound and lower bound. So this is working as expected. Alright, so last but not least, I want to show the RTL view of this circuit. So right now I've already opened Quartus. I'm going to press OK to compile this code. Let's see it, make sure that it compiles. Okay, there we go. And it's done. So now what we can do is we can go to Tools, we go to Netlist Viewer, and then we go to RTL Viewer. So this is what the circuit looks like now here. We see that we have 3 input variables. These are all 1 bit. Let's see if I can zoom in. We have the clock, the clear, and the load right here. As we move down, we have the reset right here. And then by default, the input is 4 variables, 4 bits, rather. So we have here D. So let's take a look here. D is the variable that we choose when we want to load a value. And we need to remember that D needs to be in between the upper bound and the lower bound here. And so here are also the upper bound and lower bound. Let's keep going. And then here we have the enable and then the up down variables. So this tells us, this is basically allows us to pause the counter if we want. And this variable allows us to make the counter go up and down, up or down, depending on if it's 1 or 0. So this is the overview in here. And in the output, let's take a look at the output. We have the min tick and the max tick that I had declared, and then we have the Q, which is the final output. And then we see that we are using 4 flip-flops. So the beauty about this is that if we instantiate this circuit with a bigger number of bits, 5, and then this will automatically adjust the number of flip-flops here on the right hand side that we have here, right here. So this is one of the great benefits of coding in SystemVerilog.